Okay, let's continue.
So, last time we were looking at guys that look like sine of n, cosine of n x. And I believe we dealt with all cases except, I don't know if I call the case 4 or 1, 2, A, B, C, D, or 1, 2, 3, 4, it doesn't matter. The one where both are even. Okay. So both m and n are even. What do you do in the case that both n and n are even? Well, basically, you do use another trig identity, but it's not going to be the Pythagorean identity usually, or at least not only. You're going to use, I want to say the half angle formula, or double angle formula. It's the same thing. I never know which one to call it at which time. Half angle formula. And you might have remembered those. Hopefully you do. These are. Does anyone remember what the half angle formulas are? Yeah?
Sine squared x is equal to 1/2 times 1 minus cosine 2x.
1/2 times 1 minus cosine 2x. Alright, so that's 2x in the angle. Yeah. That is the half angle formula for sine. And we also have 1 for cosine squared, which is sort of the same thing, but it's plus. Right, basically use the double angle formula for cosine. Cosine of 2x is equal to cosine squared minus sine squared. You can use the Pythagorean identity like those to actually solve for either the sine squared or the cosine squared, and you end up with these guys. So these are the half angle formulas, and these guys are useful if we have both even. So let's actually look at some examples here. How would you integrate sine squared? How would you integrate sine squared x, cosine squared x? I'll say cosine squared, but if you know how to do sine squared, cosine squared is not a big deal. So, you have sine squared. This one is pretty straightforward. You're literally going to replace it with that. So we have the integral of sine squared dx. This is going to be equal to 1/2 1 minus cosine of 2x dx. This is going to be 1/2. Let's actually start doing it at this point. So the integral of 1 x, integral of cosine 2x.
Negative sine 2x. Or negative
One.
sine, yeah, 1/2 sine.
Negative 1/2 sine 2x. Okay, and that was done using a substitution, u equals 2x, but at this point, that's kind of a substitution you should be able to do in your head. Whenever you're substituting anything linear, you pretty much divide by the coefficient of the x term, the slope. That's it. Nothing else to do here. If you have a situation like this, though, it can get somewhat annoying when you have several of these guys bouncing around. So if we were to go to b, sine squared x, cosine squared x, there are actually a couple ways we could do this one. Okay, so here's one way. One thing you can do is you can realize that sine squared x cosine squared x dx is actually equal to, well, sine x times cosine x all squared. So that's the first thing. Now, this should remind you also of a trig identity. Sine times cosine, remind you of anything?
Sine 2x.
It reminds you of sine 2x. What is sine 2x equal to?
2 sine cosine.
2 sine x cosine x. So that inside here is actually 1/2 of sine 2x. Now, this is going to be squared. So basically what you have here is you have 1/4 times the integral of sine squared 2x. Now, we're kind of in the same situation as before, except now our angle is 2x, but the same idea actually applies. I'm going to apply the half angle formula. So this is going to become 1/2 of 1 minus cosine of 4x, because you're going to double the angle. So this ends up becoming 1/8, 1 minus cosine 4x. And so now this is going to be 1/8 times x minus 1/4 sine 4x. Let's see. That's going to be that one. Another way, which, faced with this, I'd probably do it this way, but there's another way that you could potentially have seen it, and there are other times where you can't really get away with doing this. You're going to have to like multiply stuff out, and it gets kind of annoying and all that stuff. So there's another way. So you have sine squared x, cosine squared x. Like I said, John, I wouldn't do it for this one, but it's something you can do and something you might think about doing in other similar situations. Is just apply the half angle formula to each one separately. So you'll get a 1/2 times 1 minus cosine 2x here. You get a 1/2 times 1 plus cosine 2x over there. You can factor out the halves. You'd end up with a 1/4 on the outside, and you'd end up with something like 1 minus cosine 2x times 1 plus cosine 2x. And then of course you can multiply that out. And that's just the difference of squares actually. So that's just going to be 1 minus cosine squared 2x. Now you could flesh this one out again, or you can just remember that 1 minus cosine squared was sine squared. And the rest is history. So you can actually see it another way. So sometimes you can like collapse things and use other identities before applying the half angle identity. Sometimes you can just apply them right at the beginning. Sometimes when you multiply out, you get something nice. Sometimes though, like if this was a 4th power here, this would be a squared power there. You'd have to multiply out and FOIL out, and you get a bunch of things that you have to regroup. And some apply half angle formula some places and not others. Maybe I'll just so it doesn't look all that trivial. Maybe I can do that example so you can kind of see how it would look. Let's look at that one. So here I would have 1/2, 1 minus cosine 2x. Over here I would have 1/2, 1 plus cosine 2x, right? That will give me the cosine squared, and then I'm squaring that, so that's what that's going to look like. And now it's just a matter of very annoying algebra. The half square is going to be a 1/4 times the half over here, that's going to give me the 1/8. This is going to be 1 minus cosine 2x, and this is going to be 1 plus cosine 2x squared. At this point we also have a couple options. I can take one of the factors of this, multiplying that, and I would end up with the sine squared 2x left over with the other factor over here. I'm not sure it's going to be any prettier. And so this would come down to sine squared 2x plus sine squared 2x times cosine 2x. So here just it's a matter of multiplying out. Now equals 1/8. So this one here, I would apply the identity again. So we get that integrated. I'd probably split these up. I'll let this hang out here for a second. I'll ask you about that in a little bit. There should be a 1/8 over here. I would get now a 1/16 times x minus 1/4 sine 4x. What would happen over here? What do you think you would do for this integral over here? Yeah.
You can break sine up into 1 minus cosine squared 2x.
For what purpose? And then what, multiply it out?
I mean, I didn't think that's what I heard.
Oh. Okay. Other guesses? Yeah?
If you do u substitution for sine,
Yeah.
then
Then you get the
Cosine.
cosine. Right.
Will
So
go.
now this is in a situation that was covered by a previous case. Here the power of cosine is odd. So I have an odd and even power. So at this point I'm thinking like substitution. I wouldn't even think of half angle formulas again. So at this point, like you'd say u equals the sine of 2x. Your du is going to be 1/2 cosine 2x dx. And so this is end up going to be 1/4 sine cubed 2x over 3. So you sub there, because I'm now bumped into another case, right? So again, when there are not many of them, it's not that big a deal. But when you start combining these guys together, it can start to expand on itself, and then you might have to use several techniques all at once. But that's kind of going to be the name of the game. A lot of integrals. As we go on further, it's going to be like that, where we're going to start off simple and it just kind of branches out, and we have to use a different technique on this part than on that part. And once I teach you some more techniques, I'll kind of show you how to actually look for them and look at them and what to try first, second, third, etc. But for now, any questions on these? I mean, we're just doing integrals using trig identities. They don't. The sines and the cosines aren't that bad. Secants and tangents can be annoying though. Let's do that situation. So here's another type of integral. Secants, products of secants and tangents. Now, like I said, and I'll skip these because of this reason that I mentioned before, if you look at cosecants and cotangents, they're very similar. So I'm not going to test you on them, nor are going to even cover them. The idea is, if you really understand secants and tangents, all the identities here, techniques here will be kind of analogous to ones over there. So here I want to cover 3 cases. I said 3 and then wrote down 3. So this is when power of secant is even. The next one's greater than or equal to 4. And the next one is if power of 10 is odd. So these two cases are kind of are nice to deal with. Probably all of the cases I throw in another one. And pretty much what I'm going to say for that is they can be tricky. You kind of just you kind of try something and hope it works out. Yeah, I mean, with sines and cosines, it's very
That's what I do with everything.
relatively easier. It's like, yeah, there's no like general procedure, but we have general procedures for the first two. So, you have examples for yes, so let's actually cover those. So, in the first case, does secant even have to be odd there? The power of secant doesn't even matter in this case. However, you do need a secant to be around. And I think that'll be good enough. So those two cases, we have pretty standard ways of dealing with those. In other cases, and I'll give you a few examples here, you kind of just have to figure it out as it goes. Try to apply some trig identities, maybe some other integration techniques. So yeah, that one's going to take some practice getting used to. But in general, I won't give you anything too crazy over there. So let's look at case 1. So how do you do with case 1 when the power of secant is even and at least 4? Here is what you do. You save secant squared, right? So remember, just like last time, you'd save a sine or a cosine. Here we're saving a secant squared. You're going to then change all other secants to tangents using. Now remember, we had that identity 1 plus tangent squared equals secant squared. So there's another secant squared, or a secant to the 4th, or a secant to the 6th, or a secant to the 8th. I can use this identity to change those guys. Then we can finish off with a substitution. Let u equals tangent. So you have to change everybody else to tangent. Remember, derivative of tangent is secant squared, so the du is going to be that secant squared that you saved in the beginning, and everything else should be fine. After that, you should get a polynomial and it should be fine. Let's actually do a couple. So, examples here. Let's talk about secant to the 4th. Now, if you have just secant squared, you know the integral of that is tangent. So, secant cubed is an odd power, so it isn't covered by this case. So this is the smallest case where this technique I just told you is applicable. And the other one, I want to do secant to the 4th times tangent squared. here, you have secant to the fourth x dx. So the power of secant is even and at least 4. What I'm going to do is I'm going to factor off a secant squared, save that because that's going to end up being my du down the road. Now what I'm going to do is I'm going to change all other secants to tangents. It's going to be 1 plus tangent squared. And now if I let u equals tangent, your du is going to be secant squared dx. And so this integral just becomes 1 plus u squared du, which is fine. I mean, that's u plus u cubed over 3 plus c. This is going to be u equals tangent. Tangent x plus tangent cubed x over 3 plus c. And you can differentiate that, you'll see that you get secant to the fourth. Okay, what do we want to do here?
Save the secant squared.
Okay. So you have a secant squared, tangent squared, secant squared. Save one of these guys, put them in the back. Next step.
Change the sequence to tangent.
Right, so this one you're going to save. You're not going to do anything. You're going to change this to tangent, and of course that's by the trig identity, 1 plus tangent squared. So what's that going to look like? At this point you can let your u equals tangent. You're going to end up with the integral of 1 plus u squared times u squared du. This is the integral of u squared plus u to the fourth du. This is equal to u cubed over 3 plus u to the fifth over 5. We kind of see where this goes. So this is tangent cubed over 3 plus tangent to the fifth over 5 plus c. And there's that. I'm kind of bored of these, I want to get them over with. On the other hand, I don't want to because the next thing I have to teach you is trig slope. But the one after that, that's going to be interesting, like partial fractions. I kind of like that one. And besides, there's some nice tricks to go along with it. Yeah, so that's that one. Case 2. This was when the power of tangent was odd, secant present. Power of tangent of an angle, is odd, and secant is present. And the power of this secant actually doesn't matter. It could even be a fraction if you wanted it to. It wouldn't really matter. So what you do here is you would actually save secant x tangent x. You would then change all other tangents to secants. Again, you're going to use that same trig identity, the Pythagorean one. 1 plus tangent squared equals secant squared, which means you can write tangent squared as secant squared minus 1. And then you're going to do another substitution. Finish with u equals secant x substitution. I'll give you some examples there. So A. Secant x tangent cubed. Secant cubed tangent cubed. So again, once you're in this situation, for the most part, it's straightforward. Gonna say what you have to say, do that change, do the substitution. It's kind of following your nose kind of thing. Secant x tangent cubed dx. So here, our tangent is odd, and there's a secant hanging around, which means I can pull out a secant times a tangent. If the secant wasn't there, I'd kind of be in trouble. But I believe tangent cubed was one we actually did already. I believe we did that last class. So I actually know how to deal with that if the secant wasn't there. So all I'm going to do at this point is there's going to be a tangent squared left if I pull off the secant tangent. I'm going to change that tangent to secants. This is going to be secant squared x minus 1. And now, if I let u equals secant, this is going to be u squared minus 1 du. The derivative of secant is secant tangent, that's going to be my du. And just plug those in. And if, so u cubed over 3 minus u plus c. And this times RU was secant, so that's secant cubed over 3 minus secant plus c. That one. We'll get some interesting cases with secants and tangents after this. Let's just get through the last example here. B. So power tangent is odd, and we have secants present. So what I'm going to do is I'm going to factor out a secant and a tangent. Then I'm going to change all the tangents to secants, because what I want to do is equal secant so that I get that secant tangent du. So I'm going to leave this secant squared here. I'm going to change that tangent to secant squared minus 1. And then I'm going to do that u equals secant. So this is going to be u squared minus 1 u. So 0 u to the 4th minus u squared du. This is going to be u to the 5th over 5 minus u cubed over 3 plus c, which is secant to the 5th over 5 minus secant cubed over 3 plus c. Any questions? Okay, that should be fine. Okay, let's look at some interesting ones. Tangent cubed, I feel like we did already. Here are some other ones. other cases. Are tricky. Try something. Hope it kind of works out. Of course, they're going to be, after you start doing a bunch of them, you start to get kind of a feel for the kind of things you will try. A nice one that can let you know what the possibilities are is integral of secant cubed. Now, surprisingly, this guy happens to show up all the time. It just happens to be a form that shows up all the time for some reason. So even after we derive this, I'd probably recommend that you memorize the integral of this. It's going to be a very random thing to memorize, I know, but like in Calc 3 and Calc 4, like you do, anytime you're doing a trig sub, somehow this guy shows up all the time. I don't know why. I've never really looked into it. It's just like, after keeping statistics, it's just, why do you always have to end up doing this guy, secant cubed? So it's another one of those kind of famous integrals, and the strategy for actually computing it is actually well known. There are several ways to actually do it that a Calc 2 student would get, but the other ways, I haven't taught you the techniques that you need to understand them yet. So we're going to do using techniques that we've already had. So Calc 2 is your last math class. You can probably get away with not memorizing this one. If it isn't, it's probably going to show up in the next classes in the most oddest of times. Maybe any guesses for how to approach this one? We have an odd secant. What can we do with it? Derivative of secant is secant tangent. Derivative of tangent is secant squared. None of the other trig functions really give a secant or a tangent when you differentiate them. So first step would probably be, like I said, try something. Okay, so I know that secant squared is a thing that shows up in my derivative rule, so I probably want to expose that at least. Now what? Now what do you think you can do at this point? Now, another thing, change the cosines. That's an idea that works sometimes. You have a weird trig function, change everyone to sine and cosine. In that case, usually, those cases are usually easier to handle. But then 1 over cosine cubed. Have you ever considered 1 over cosine cubed, what that would be like to integrate? How do you go and integrate that? U equals, well, you could actually get somewhere with that, but again, we don't have the technique. Something that you could try here. Multiplying top and bottom by cosine, you could then write this as 1 minus sine squared squared. That would end up becoming, well, basically 1 over 1 minus u squared squared. Now that in and of itself is kind of tricky to deal with. Partial fractions would be how you deal with that. So at the moment in theory we don't know partial fractions, so that's kind of a dead end at this point. What else would you think? What are you going to try? What do you have? Substitution is not going to work, so that's off the table. What else did we learn? Yeah?
The trig identity.
Which trig
So
identity?
secant squared x equal 1 plus secant squared x.
Okay, let's try that out. Secant, let's see how 1 plus tan squared. So So that's going to become secant x plus secant x tangent squared x. Okay, then what? Well, the integral of secant we know. We actually derived that last time. That's ln of absolute value of secant x plus tangent x. What about this guy? How would you do with that part? There's a secant tangent right there, you can factor out, but then you're left over with a tangent. What are you going to do with that? Change to the radical of secant squared minus 1, then do a u substitution, then now you have to integrate the radical of u squared minus 1. Do we know how to do that? Yeah.
Could you separate the two? Secant x, integral of secant x plus integral of secant x times.
Yeah. So, yeah, that's what I mentioned. So this, by itself, we know how to deal with. That's ln of absolute value secant x plus tangent x. But then if I were worried about this part of the integral, yeah, that's sort of that end. Traditionally, integration by parts would be the step after this. What do you think the parts are going to be? Now, that automatically is like, what? Integrated by parts? Liotte doesn't even seem to apply. We have trig functions all over the place. But integration by parts is traditionally what we would do next. What do you think the parts are going to be? There are two options, right? Turns out that u equals secant, and dv would be the secant squared x dx.
And you're gonna put the same thing that you just had.
How do you- Well, you're going to have, what are you going to have? du here is going to be what? Secant x tangent x, right? Right, now I chose dv to be the secant squared because I know integrating that will actually lower the power, right? Because the integral of secant squared is what? Tangent. So now, if I do, so the integral of secant cubed dx, if I do the u times v minus the integral of the v du, we end up with that. Now, that was the guy we saw last time. And here's what we're going to do. I'm going to change that tangent squared. Was that the guy we saw last time? I don't remember. I'm going to change that tangent squared to secants. Which might sound crazy initially, but you're going to see something afterwards. How do I change tangent squared to secants? It's going to be secant squared minus 1.
Squared. Oh, yeah,
No, it's secant squared minus 1. What can I do with that? If I multiply this out, this is going to be secant cubed x minus secant. What do we do now?
Can separate it for that.
Right. Hey, that's the original guy. So this becomes secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. Now what you can do is, this guy is the same as that side. I'm going to bring this over, I'm going to get 2 of them, and I'm going to divide by 2. So this means I would get the integral of secant cubed is going to be 1/2 times this, which at the end of the day now becomes 1/2 secant x tangent x plus ln of secant x plus tangent x plus c. And that's actually what the integral of secant cubed is. So yeah, that's a formula you can memorize now. Like, this is just something we know now. And it's worth remembering, especially if you're going into multi or higher. Like I said, for some reason that guy shows up a lot. Yeah.
Would this have worked with the tabular method? Because wouldn't you end up getting back to the same part and then you could...
Yeah, like I said, whenever integration by parts works, the tabular method also always works. It can always work in all cases. The tabular method would be... You wouldn't be able to bring the tabular method to the completion by doing this, because for the tabular method you'd have to escape at this point to make this change. Like, the tabular method doesn't apply any trig identities in it. So you'd have probably stopped it here, because doing it a few more you'd realize that probably you don't really get anything else out of it. I've never completely done it by the tabular method, but I'm thinking that you probably need to exit here. I have to check. You'd have to write it out. But yeah, in general, the tabular method is integration by parts. It's just another way of writing it out. Yeah, but that's like this is like the standard way to actually derive this integral, the integral of secant cubed. And we'll probably see a couple of examples where you'll see it popping up, but it actually pops up outside of this class all the time in all sorts of applications. Yeah, I feel like the other integrals that I asked here, we've already actually dealt with. Okay, let's do it. Trig substitution. Okay, short for trigonometric substitution. And basically, this is a situation where you don't start out with trig, but you introduce trig in order to take advantage of some trig identities, right? So you apply these to non-trig integrals to change them to trig integrals. And kind of based on the following, right? So there are some identities that we know of. Very nice guys. So here is like a table. So here's the expression that we use. So you might see this guy showing up all the time. For example, x squared plus a squared. Here, a is a constant. And we kind of take note of this guy, especially if there's a radical involved, especially if you're seeing something like the radical of x squared plus a squared underneath the radical. You might start thinking trig sub. There are situations where you won't think trig sub, but I'll cover those separately. Now, what trig identity kind of reminds you of this? Well, whenever you see this expression, this is the substitution you're going to make. You're going to substitute x equals a tangent theta. Now, why would you substitute a tangent theta? Because there's an identity that you're thinking about. Identity. Right? that identity is going to be 1 plus tangent squared theta equals secant squared theta. In fact, this means that if you have a squared plus a squared tangent squared, this will actually simplify to a squared secant squared. Do you see that? In other words, if you have a squared plus a tangent all squared, this simplifies to a secant squared. And the reason is, in factor out the a squared, you'd have the 1 plus tangent squared, which turns to secant squared. So in short, you can take a sum of two things and collapse it into one thing. And that can be convenient, especially if you're dealing with a radical, because you can't distribute radicals across sums. So if you can turn the thing underneath the radical into one thing, that might be useful. And trigonometry happens to be a nice way to actually do that using the Pythagorean identity. So basically, if I have a squared plus x squared, replacing my x with the expression a tangent theta can cause something like this to happen, because it's based on this identity. Now, there's another expression that would be important, is of course the a squared minus x squared. So if you see that expression popping up in an integral, especially if they're like radicals around, you can take advantage of another identity. You can make a substitution x equals a. Now typically what we do here is a sign identity, a sine theta, so that you don't have to worry about the negative sign when you take the dx, when you actually differentiate both sides. But a cosine theta can work as well. I'm pretty sure your textbook only mentions the sign, but either one can work technically. Traditionally we always use the sign, so we don't have to worry about the negative sign popping up from differentiation. And of course what you're thinking of here is something like 1 minus sine squared equals cosine squared. And so if you have an expression like a squared minus a sine theta all squared, that would collapse into a squared cosine squared theta because of this identity. Right? So if you let your x look like a sine theta, you can kind of do this maneuver. The other expression is the other way. You have x squared minus a squared, especially if it's in some sort of radical. Then x equals a secant theta is going to be kind of the knee-jerk reaction here. And it's again because we're looking at this one. We're looking at the fact that secant squared theta minus 1 equals tangent squared theta. So this should tell us that if we have like a secant theta all squared minus a squared, this would collapse into a squared tangent squared theta. Because again, we can make this a squared secant squared, factor out the a squared, you'd end up with secant squared minus 1, change that to tangent squared, and you get this. So far it might not seem like a big deal, but actually plugging in the identity isn't the bad part. It's when you have to undo it. Because remember when you do a substitution like u equals blah blah blah, eventually at the end you have to kind of change the u's back to x's. Remember that? So once you use this to change an integral into thetas and trig functions, you're going to get the answer in terms of trig functions, which the previous section was supposed to teach you how to do. You're going to get an answer in terms of theta. Now you are going to have to turn that answer in terms of theta back to x in general. And that's really annoying with trig sub. So using the above, we can sometimes change integrands into functions of theta to compute that Now, to put back the original variable, to back substitute, you would use solgato. I just like saying solgato. It just sounds, yeah, it just feels like that's how it should be said to me. That's how I've always said it in my head. Okay, solgato. Okay, so basically what that means is, so for example, in the x equals a tangent theta case, what you can do is you can solve for tangent, get x over a. What you do is you think of the a as the opposite, the x as the opposite, and a as the adjacent, right? So tangent is opposite over adjacent. And what that means is you can construct a triangle where x is over here, that's over there. Pythagoras' theorem will tell you that that's that side, which happens to be the convenient expression that we mentioned earlier. And then, based on whatever trig functions are in your answer, you can use this triangle to convert them back. So if there's a cosine theta ending up in your answer, well, you know that cosine is going to be adjacent over hypotenuse. So you replace that cosine with a divided by the radical of blah, blah, blah. If there's a sine in your answer, you know that's opposite over hypotenuse, so that's going to be replaced by x divided by blah, blah, blah. And you can know all the trig functions by taking reciprocals of these, and etc. If there's a tangent that appears in your answer, you know you can deal with, replace the tangent simply with the ratio x over a. If there's a theta, like a lone theta in your answer, well, you can solve for theta here to get theta equals tan inverse of x over a, and you replace all of those. And yeah, that's kind of the idea. So you kind of remember these expressions in terms of these convenient trig functions. Once you actually use these to convert them, you can get an integral that hopefully is easier to compute. Once you compute it though, you'd have to back substitute. I probably shouldn't have erased that. That was the last thing I actually wrote. For example, in the x equals a tan theta case, this leads to this triangle. So you're going to have to be drawing triangles all over the places and using Pythagoras' theorem. And then you can find all trig functions from here. Also just note that your theta itself will be considered as tangent inverse of x over a. By the way, we actually have a formula for tangent inverse. You guys remember that we had the integral of 1 over 1 plus x squared dx is equal to tan inverse? You guys remember that? Let's actually derive that. We can derive that with this. So let's say you didn't even do the inverse trig function in Calc 1. With the power of trig substitution, you can actually derive that. So here's an example, 1 over 1 plus x squared. Now, I expect you to know this by heart is tangent inverse, but let's just, as an easy example to try to ease into this technique, let's actually do one that we know what the answer is. So here, notice that you have the kind of expression a squared minus x squared. So one thing you can here is note, we have a squared plus x squared, where your a is equal to 1 in this case. So a trig sub can be applied here, and again, with this, I expect you to know this by heart. Don't do a trig sub to do this guy. It's just for illustration purposes. Okay, so what I would do here is set x is equal to 1 tangent theta. Now, so it's just like, it's going to be like a regular substitution. So I'm going to have to find a dx, and I'm going to have to plug everyone in. So now I'm going to differentiate. This is going to be dx is equal to secant squared theta d theta. Right? And now I'm going to plug everybody in. Okay, so this is going to become 1 plus, well, over here this is tangent squared theta. But you can actually interchange this expression with the secant a squared secant squared theta right away. But, okay, so that gets replaced, x gets replaced by tangent, the dx gets replaced by this entire thing. So here, I end up with secant squared over secant squared, because 1 plus tangent squared is secant squared. Well, that's just the integral of 1 d theta. And then you might ask, well, that's just theta plus c. We know that x is equal to tangent theta. This implies that your theta is actually the tangent inverse. So that just gives you tan inverse of x plus c. In fact, you can sort of derive a formula in general here. So let's actually just do that. Very similar. I'm going to go through this very quickly because I just went through that one, and this isn't a complicated example in general. If you have the integral of x squared plus a squared, like in general, right? So that doesn't have to be a 1. What you would do is set x equals a tangent theta. Your dx is going to be a secant squared theta d theta. So you have 1 over a d. I'm just going to put that in. So what's going to happen now is I'm going to have 1 over, this is going to be a squared tan squared plus a squared times a secant squared theta d theta. You'll notice that this here, the a is a constant, that can factor out. There's also an a squared in the denominator, that can factor out. And I would end up with the secant squared theta over secant squared theta. So I end up with 1 over a times the integral of 1 d theta. This gives you 1 over a times theta plus c. And then my theta is going to just be solve for a tangent, get x over a, then take the tan inverse of that. So this is 1 over a tan inverse of x over a plus c. Now if you look in the back of your calc book, there will be, in the formula table of formulas, there is this guy here. So this is where they got it from. So for example, if someone asks you, what is the integral of 1 over x squared plus 9? We now know that that's just going to be a third tan inverse of x over 3 plus c. Here's that table. Let's do something a little more interesting. Let's look at this one. X squared over the radical of 4 minus x squared dx. Let's finish copying. Now the first thing you're going to think of is, well, does this integral look like a basic rule that I know? The answer is no. Then you're going to probably think of, well, can I simplify this so that it looks like a basic rule I know? The answer is no. Then you're going to try, well, can a substitution work? And the answer is going to be no. And the reason is, probably the best thing you would want to substitute here would be the 4 minus x squared, because that's what's making it complicated. The derivative is going to be minus 2x. Now the derivative is going to get rid of one of these x's, but it's going to leave the other one over. And if you were to solve for that other one, you get a radical, you get something very similar to this. You'd end up in the same situation. So the substitution is also not going to be very useful. However, I can notice that this looks like an a squared minus an x squared. In fact, this is 2 squared minus x squared. So that reminds me of, hey, this guy actually looks like a trig sub. So what I can do here is set x equals, so once you have this minus that, what is the typical substitution?
X equals a secant theta.
When you have a squared minus x squared?
Oh, x equals a sine theta.
A sine theta, right? Because it reminds me of 1 minus cosine squared. So the a is 2, and then I'm going to put sine theta. So that would be the substitution.
That's you.
Right? Now you can go home, you can try that a regular substitution here isn't going to help you much. But that would be how you start. Now you're going to differentiate. Derivative of sine is cosine theta d theta. So now you're going to go back over here and you're going to plug into this integral. Now your x is 2 sine theta, so your x squared is going to be 4 sine squared over, this is going to be the radical of, now if your x is 2 sine theta, then the denominator would become 4 minus 4 sine squared. You could factor out the 4 to get 1 minus cosine squared. So this is going to be 4 sine squared in the denominator. Times the dx, that's going to be 2 cosine theta d theta. So that's what this integral will transform into. Any questions so far?
Shouldn't it be 4 cosine squared?
Where?
The
Where?
denominator?
X is 2 sine, yes, the 1 minus sine squared is cosine squared, so that's a cosine. Now, at this point, we'd simplify these. Technically, you'd get an absolute value here, but let's pretend the angle keeps everything positive, whatever. So, we're going to have 4 sine squared theta divided by, well, it has to be positive for the radical to work in the first place anyway. So I take the square root of that. Times 2 cosine theta d theta. So that's what you get. Now what happens is that this one actually kills that one. And now we end up with the integral of 4 sine squared theta d theta. But hey, we learned how to integrate that today. That's useful. So what we're going to do now is like the half angle formula. That's going to end up with 2 times 1 minus cosine 2 theta d theta. And then that's going to be 2 times theta minus 1/2 sine 2 theta plus c. So that's the answer in theta, right? So we did our trig sub because we saw that special expression right there. And the 3 expressions I gave you on the board right here, you just have to have those memorized. They're the ones that you'll be looking for to pop up. So that like an x squared plus an a squared, or an x squared minus an a squared, or an a squared minus an x squared. These guys you can do trig subs. Now, here's the answer in theta. Now we have to go back to x. How are we going to get back to x? Well, we're going to use solve. So it's like the answer is right there, but you can't just in one line like flip it again and just like, oh yeah, this is the answer. No, you have to go through this whole other process. Okay, so x is 2 sine theta. This means that my sine theta is going to be x over 2. I'm going to think of the top as the opposite. I'm going to think of the bottom as the hypotenuse because of SOHCAHTOA. And then this is going to lead to a triangle. This is opposite, this is hypotenuse, which means that this, by Pythagoras' theorem, is going to be the square root of the hypotenuse squared minus the other side squared. Okay. Now, I'm going to note that my theta itself, because there's a lone theta just sitting right here, I solve for sine theta. The theta itself is just going to be the sine inverse of x over 2. So that's the theta. As for the sine 2 theta, how are we going to fix that one? How do I convert the sine 2 theta back?
Would it be the same as sin x?
No, because x isn't 2 theta, right? X is this. X is 2 sine theta. What are we going to do with the sine 2 theta?
Two sine theta cosine theta.
There's a trig identity for it. This is the double angle formula. Is that useful? Well, not sine and cosine, which I can get from the right triangle. So the sine of theta, well, we actually already know that that's x over 2. Now the cosine of theta is just adjacent over hypotenuse. So the adjacent is this. And the hypotenuse is that. One of the 2's would get cancelled, and so basically I get a half x times the radical of 4 minus x squared. Now, this implies that the actual answer for the integral is going to be 2 times theta, which I know is this, minus 1/2 sine 2 theta, which I know is 1/2 of this. That's the answer. And again, even this example isn't as bad. It doesn't show you how bad these things can actually get. Because sometimes you can, once you do the transformation to trig functions, this thing doesn't have to be a walk in the park right here, right? You could end up with one of those weird secant tangent forms that's like, there's no standard approach. You have to figure out how to do this, get there. After that, you still, oh my god, now I have to go through all of this to get to the answer in the final answer, right? For this reason, if something like this has limits, what you would do is not do that, like just change the limits and plug it in at this point, right? So in my Calc 1 students, I told them, oh, remember in Calc 2, there's going to be something called trig sub, where I'm going to tell you, here's where you always change the limits. Now you guys know what I was talking about. So yeah, this is kind of trig sub. Maybe I'll give you some more examples to actually try on your own. And then I will give you some recommendations on how you're going to want to go about applying trig sub, knowing when you need to versus when you don't need to, and some more examples. So try these out. We'll do them on, we'll go through them on Thursday, and some recommendations, as well as maybe start partial fractions if we have time. So let's try this one.
Yeah.
See you on Thursday.
Got you.
Yeah.
Yeah.